Okay, let's go and get started for the day. Today we're going to look at a type of real-world synchronous communication that's used all over the place in all kinds of systems. You've probably actually used it today without knowing it, but this is synchronous communications with a kind of a standardized method called SPI. And so let's go and dig into that. So first off, back to synchronous communication. A quick review of that. The idea with synchronous communication is they have this shared clock signal. So in other words, there's a clock that ticks, tick, 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 up and down. And both the sender and receiver have access to that clock. They can both see that clock, and it has to be a shared clock, meaning that it's not like the times were just set the same, or they're using a crystal that has the same frequency. It's actually the same signal they're both using. Now, synchronous, as we talked about previously, ironically, that makes them less sensitive to changes in timing because they're looking at the same clock. All that matters is when it changes state. Does it go low to high? Does it go high to low? And so, since they're both looking at it, it could go low to high, and then a long time later, go high back to low, and vice versa. All that matters is they're both looking at that same clock. That's what makes it synchronous. So thus, the receiver and transmitter both have to have access to that same clock signal. And usually it's the case where the transmitter generates that clock. In other words, it's the transmitter that says, hey, here's this data I want to send, tick, 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 tick. But as we'll see with SPI, that it's really both a transmitter and receiver at the same time, and they're both looking at the clock. But one of the ends, in this case, in SPI terminology, called the master, is the one that generates the clock. The other devices that are connected to it just look at the clock or use it. So that clock might have a separate channel or be combined with the data on a single channel. In other synchronous systems, in SPI, it has its own separate signal, as we'll see here in a second. Okay, so this is the idea, that extra clock signal being used. We've seen this before. No framing bits, just the clock signal. We're going to see that in SPI as well. All right, so let's dig into SPI and some of the specifics on that. And SPI stands for Serial Peripheral Interface. So it's a serial communication technique. It's synchronous as well. But it's generally was intended to be used for peripheral components in some sort of embedded system or in some sort of product to communicate information both to the processor from that sensor system or that device, and then from the processor to those devices. So it's a way to get data both from the processor to the devices, from the devices to the processor. So considering an embedded system like a smartphone that has memory, it's got a CPU inside of a system like this, but it also has a number of peripheral devices. For example, it has a touch screen, it's got a fingerprint sensor, it's got these buttons on the side, it's got a speaker when you put it on speakerphone and listen. It's got a microphone that when you talk, it can hear things. It's got network connectivity of several forms, GPS. There's a lot of stuff in there. So the touch screen itself, inertial sensors to detect whether it's landscape or portrait, or I'm moving it around, GPS, Wi-Fi and Bluetooth, a camera, so you can take pictures, and also the SIM card that's in here, or the memory card that you could actually put in to expand the memory if you wanted to. All of those peripherals in there need to talk and get information to the processor or get information from the processor. So we need a way for those to communicate inside of this system. And that's what SPI provides. So SPI, it's helpful because it's a standardized way that allows integrated circuits to exchange information with the processor in some way. And there are other systems that are generally also in play in these things. There's another one called I2C, or I2C, which stands for Integrated Circuit Bus, also sometimes called IIC. But notice this is usually pronounced I2C, or I2C. And then SPI, the one we're looking at today. Both of those are synchronous communication systems. We're going to look at I2C next lecture. Today we're going to focus just on SPI. But they're both synchronous communication systems, and they're both designed to have chips talk to each other in things like embedded systems. So today we're going to look at SPI. So let's dig in and take a look at some details of that. All right, first off, SPI is synchronous. And that means that it has a shared clock, but it was designed to be used or for use in embedded systems and other kind of short-range communication applications. So it's a way to have not something talking, one device talking to another device that's on the other side of the city or country. It was designed to have a chip in a device talk to the processor in the device. So if you have a laptop, there's some SPI communication probably going on in there. If you have a smartphone, I can guarantee there's SPI communication going on in there. If you have even something simple like a digital voice recorder, there's probably a form of something like SPI communication going on in there. If you have a Wi-Fi security camera or something like an Alexa, I can pretty well guarantee there's SPI going on inside that thing. Now, the main thing here is there are a lot of different types of devices that communicate over SPI. You probably used some of them today. If you used your smartphone and used the touch screen, or used your smartphone and talked on the phone, or watched a YouTube video and it showed up on played audio, probably some SPI or a variant of something like SPI going on there. SPI is full duplex. It uses a master-slave architecture. And if you remember back to the lecture where we talked about what full duplex means, that means it can transfer data in both directions at the same time. So it can communicate from, in this case, the master to the slave. It can convey data. But at the same time data is going from the master to the slave, data can also be going from the slave back to the master. So full duplex. In other words, data is going in both directions at the same time. And again, in SPI, one device is the master, and then there can be one or more slave devices. There are some SPI systems or variants that have a multi-master configuration where there are multiple masters and they can take on the role of the master and talk to the slaves and then switch. But for the most part, in most systems that you see, most embedded systems like this, one of the devices is the master, the other ones are slave devices. So let's take a look at how it works. Let's look at the wires that are there and how that actually functions. Okay, so here's the idea. SPI uses a minimum of 4 wires to talk from a master to a slave. And the wires, those 4 wires are as follows. SCK is usually labeled, that's the serial clock. So that's the shared clock signal we're talking about. And notice the direction of that. It's coming from the master going to the slave. Also notice that we have MOSI, which is the data coming out of the master going into the slave, and that stands for, it's nice in the name, you can tell which line it is because it's MOSI stands for master out, slave in. And on some devices this will also be labeled MOSI. Some devices it'll label SDI for serial data in. These are labeled from the point of view of the device itself. So this I at the end goes with that one there, in. Serial data in, master out, slave in. So the slave in goes to the serial data in of the slave device. A lot of devices will also label these MOSI rather than SDI, but they might notice that a MOSI on a chip might be labeled SDI, or some of them I've seen are D in as well, or just DI in some cases for data in. Now, MISO is the opposite signal. That's the data. Remember, this is full duplex. We have data going from the master to the slave. We also have data coming back from the slave to the master. So MISO, master in, slave out. And some slave devices that'll be labeled DO or SDO or something like that, or it might be labeled MISO, but that's the data coming back from the slave to the master. And then the final thing here is this slave select pin called SS, which is slave select, not the bar over the top means that it's an active low connection, meaning that when it's high, the slave is not selected. When it gets pulled low, the slave wakes up and does its thing. So in other words, that line can float high. Now, one thing you can have is multiple slave devices connected to a single master. Each one would just have its own slave select, but share the rest of these lines. So in other words, if I had 2 slave devices, I'd have another one of these down here. And this, all of these would be shared. The same signals would just route to that, but it'd have a different slave device. So let's say I had 2 sensors here. Let's say I had a microphone here, and I don't know, a touchscreen controller down here. Then the way I would talk to the microphone is I pull the slave select line for it low. That activates that device, and then it looks at and uses these lines while it's active. And when I pull that line back high, that device turns off and does nothing. So in other words, these just silently sit there until they're activated with pulling that slave select line low. And that what allows us to have as many slave devices as I want, as long as they have their own select line associated with them. Now, Sometimes slave select will be labeled SSN for slave select not, or this /CS, which stands for chip select, or /EN for enable. But they all kind of do the same thing. They activate the device, allow it to wake up and do its thing. Okay, internally, the way that the SPI is implemented looks like this. That basically, it's got two shift registers, and those shift registers are connected to each other, like this. That here's an 8-bit shift register, here's an 8-bit shift register, and those are in the two separate devices. Here are the 4 lines connecting them: slave select, SCK, MISO, MOSI. So again, master in, slave out connects from bit 7 of the slave's shift register to bit 0 of the master's shift register. And then MOSI connects from bit 7 of the master's shift register all the way around to bit 0 of the slave. So this is kind of like a giant ring of bits that connects together. Notice that goes in a circle. So the idea is, anytime this clock ticks, if the slave is enabled, it pushes bit 7 out on the MISO line, and it pulls bit 0 in from the MOSI line. So imagine if there's a bit pattern here. Let's put a 1 over here on the slave, and let's put a 1 over here in bit 7 on the master. As soon as I tick the clock, this 1 will move over 1 position, and the 1 that was in bit 7 will move over here. So now we'll have all zeros and a 1, 1. If we tick the clock again, that'll move again. If we tick the clock again, it'll move again. So in other words, those are all just shifting places, kind of rotating around that kind of ring configuration of that shift register. So the idea here is, and this only happens if the slave is selected, that it kind of enables the device, enables the shift register of the device. So if I tick that clock 8 times, and there are 8 bits in each of these, what happens? What's the state of the registers look like after 8 ticks of that clock? And this is a really clever implementation, super clever. But what happens after 8 ticks of that clock? If the slave select line is pulled low and this device is enabled, then it shifts its stuff out. It shifts the master stuff in. The master is shifting its stuff in while it's shifting its stuff out. So after 8 clocks, the registers have traded values. In other words, the bit pattern that was in this register is now over here, and the bit pattern that was in this one is now over there. So in other words, every 8 clock ticks, they'll exchange the data from those 2 registers. And if we put a different value in the master register and then tick the clock 8 more times, its message will go to the slave, and whatever the slave had in its register will come back to the master. Now, some chips might have larger shift registers available, like a 12-bit or a 16-bit shift register. But for the most part, there are 8-bit shift registers that are available. And that clock is basically the thing that causes them to shift 1 position. So for every tick of the clock, tick, tick, 1 bit position, tick, tick, next bit position, tick, tick, next bit position. So very similar to your previous lab. Now there is one complexity here that I haven't mentioned yet. It's on the sheet here though. That the clock can be interpreted in different ways depending on the design of the chip that's implemented this. And there are really 4 possibilities, and those are called SPI modes. Most microcontrollers or microprocessors have a way to configure what mode you want it to be. Slave devices, however, are usually designed to be one mode or another. Sometimes they'll work with 2 modes. Like there are a lot of devices that will work for both mode 1 and 3. But let's look at what those different modes mean. So the different SPI modes essentially come down to how do we interpret the clock? And there are 2 different ways of interpreting the clock. One is called the clock polarity, meaning does it idle low or does it idle high? And then the second thing that controls how the clock is which edge of the clock is used to cause the transfer, the sampling of the line. So it could either be on the first edge of the clock or the second edge of the clock. Since the clock has a phase, it goes low and high, or it goes high and low. Is it the act of it going high and then low? Is it the first edge, or is it the second edge that causes the data to be sampled? So with those 4 possibilities, we get these modes: mode 0, mode 1, mode 2, mode 3. And I can tell you from experience, almost every device that I've encountered supports like a mode 0, mode 3, one of those two. And really, a lot of times, mode 0 and 3 are compatible with each other, that it'll work either way. I have seen devices that are mode 1, but for the most part, mode 0 is what you see more commonly. And a lot of times, mode 3 devices will still work in mode 0. And we'll talk about why that is in just a second. Now, the two things that are determined that are called this clock polarity setting, usually called CPOL, and then the clock phase setting called CPHA or CFA. So CPOL and CFA determine what mode it is. And like I said, most devices are or a lot of devices are mode 0. And mode 0 means the clock polarity is 0, the clock idle is low. And clock phase is data is captured on the first edge. So let's take a little bit closer look at what we mean by those polarities here. So here's a graphic showing that. So in other words, with mode 0 and mode 1, the clock idles low. So it starts out low, and when it ticks, it goes high, and then it goes back low again. So in mode 0, data is sampled on that first edge, and in mode 1, it's sampled on the falling edge. And in mode 2, the clock idles high, data sampled on the first edge. In mode 3, clock idles high, data sampled on the second edge. Now, you might say, well, why would mode 0 and 3 sometimes be compatible? Notice this is a rising edge in both of these cases when the data gets sampled. It's going low to high, low to high. And the same thing could be true for mode 1 and 2, that it's high to low, high to low. So there are some devices that will state that they support multiple modes. But the idea is, which way does the clock idle? And is it sampled on the rising edge, or the first edge, or the second edge? And there are 4 combinations there. Now, here's another example of the clock modes that shows all of the possibilities. So CPOL 0, it idles low, and then it goes high, low, high, low, high, low, and then it finishes on low. With CPOL equal 1, the clock polarity of 1, it idles high, and it goes low, high, and it finishes on high. So notice it's just the opposite of what we would have with CPOL 0. Now notice for any of this to matter, the slave select line has to be low, or all of this gets ignored. So with the slave select line low, when we go through this clock phase, you can now see when these are sampled. So here's the cycles are labeled. MISO puts data out. MOSI brings data in, but these 8 bits that are going out match the 8 bits that are coming in. After 8 clock ticks, here are the 8 clock ticks, the data in the master and the slave will have exchanged registers. All right, devices and their data sheets will usually specify what mode they support, or they'll have a diagram that shows the waveform, and you can deduce from that what mode it is. Some devices will support multiple modes, like they'll say compatible with mode 0 and 3. All right, now, a typical SPI transaction sequence works like this. And again, we know that after 8 clock ticks, and if the device is selected, those registers will have exchanged values for one another. So most devices use 2 SPI exchanges for what's considered one transaction. In other words, the slave select gets pulled low, the master will shift out an address to the slave in the form of 8 bits. So an 8-bit address goes out. That 8-bit address includes a bit that's a read-write bit. Sometimes it also includes a multiple or single bit, as we'll see here in a little bit. But after that, we've exchanged that, and we've told the slave, hey, this is the address I want to read from you, or the address I want to write from you. The slave device then decodes, that should be an O. Let me fix that. Decodes the address. And then it looks at the read-write bit, and it decides, they sent me an address. Do they want to read from that address? And again, this is an 8-bit address where 1 or 2 bits have been removed. So we're not talking about a lot of address space here in general terms. But essentially, it looks at that and it says, if the read-write bit is set to be a read, then the next exchange is data we want to send back to the master. So we load the data of that value of that register into that shift register, and then it shifts out. So the next transaction, the master now has the data from that address. So he might say, hey, I want to read what's at address 0. The slave device will then load that into that, what's in register 0 into the shift register. Another 8 ticks from the master, and now the master has the contents of what that device had in its register 0. Now, if the read-write bit is a write, then the contents of the shift register that come through next are placed into the register that was specified. And we're going to look at this in a little more detail here when we look at the SPI transaction sequence. But after that, those two transactions happen, the entire transaction is done, the slave select line goes back high, and now the slave device is ready for the next transaction. So some devices also might have commands mapped to certain address inputs or certain bits on certain command inputs. There's a lot of variation, but generally that's the way as you say, hey, I want to read from this address, or I want to write to this address, and then that causes that device to either give data back or take some kind of action or take the data that comes next and put it into some location. It's really clever, very simple methodology that can also run really, really fast. All right, so let's look at an actual device. So the device we're going to start with looking at here is called the LIS2DH12. And it's a little tiny chip that you might find in your smartphone that acts as a accelerometer. In other words, it's a MEMS, meaning a micro machined silicon mechanical device inside there, an accelerometer, that detects how it's being moved and how it's being oriented. And that's a pretty common thing to have in a smartphone. And it's essentially how smartphones know what orientation they're in and how to switch the screen. There's a little device in here, probably one just like this, maybe even this exact one in this device. I haven't looked it up. But notice that this little chip is responsible for receiving the 3-axis accelerometer signal and then making it available over this communication interface. So the processor in the smartphone or whatever other device you're using, security system, whatever, knows how it's being moved. All right, now a couple things about this. We're going to look at the actual data sheet for this. So give me a second to pull that up and I'll switch over to it. These are from the data sheet, but you'll notice that this chip is very small, 2 millimeters by 2 millimeters, a little tiny thing by 1 millimeter. And it basically has these pins. Well, some of these pins on this, you'll notice if you look carefully at it, SCL, there's a chip select, CS, and then we have SDO and SDI down here. So those kind of match what we're used to seeing with SPI. This device also supports I2C, and you'll notice it says that down here in the features. It says I2C/SPI digital output interface. So this device allows us to use SPI to read the accelerometer data out of this and configure this thing. All right, let's give me a second to bring up that data sheet. And then we'll take a quick look at that together here. All right, so let me switch the screen over so you can see it. All right, so here's the data sheet. And you'll notice this is the same stuff that was on the presentation. But the thing that I want to look at specifically is there's a section in here that talks about the communication interfaces and talks about the SPI interface. So I'm going to go to that first. And you'll notice that here it has some timing things. Notice the clock frequency we can run this thing has a maximum of 10 megahertz. And it says it right here in the data sheet. So we can run this thing 10 million cycles per second. And if you contrast that with the rates we were getting with your Arduino lab, this is really fast. So you can get the data in and out of this thing with a pretty fast rate. In other words, with 10 megahertz, that's faster than 1 byte or 1 million bytes per second, because megahertz for 1 clock, 8 bits make 1 byte. So you can get like 1 million data points out for every second by pulling the slave select line low, and you can kind of see that here. Slave select line goes low, the clock ticks, the data both comes in and goes out. Now there's a better diagram to look at here with respect to that SPI timing. Here's the one for I2C. We're going to talk about I2C next class, so we'll probably be back to this data sheet later. But let's go to the section of this that actually talks about well, here's a circuit diagram for it. So notice you just connect the lines, the chip select, the SCL, SDO, SDI. That's the SPI interface, and then it needs a few capacitors, and that's it. It's a really simple chip to integrate and use. We just need to connect it with an SPI bus interface. Now, continuing on down through here, let's go to, this is I2C. Okay, here's the SPI interface, and it describes that. It says, the LIS2DH12 SPI is a bus slave. So this is a slave device. Let me scroll it down so my picture's not in the way. And it says SPI allows writing to and reading from the registers of the device. The serial interface interacts with the application using 4 wires. And there it labels the 4 wires, the chip select, same as the slave select and SPI, SPC, which is the same as our clock, and SDO, which is serial data out, or SDI and SDO. So those are the same as MOSI and MISO. So here's a transaction, and you'll notice that this has, when this drops low, if you count these up, there's 16 total of these blocks that go all the way up to this thing at the end. So there's these 8 here that are the address word, and then following that are the 8 that are the data in and out. And because it's full duplex, it both is going out and it's coming back in at the same time. Going out MOSI, coming in MISO. Now, they break this down into like a smaller chart here. But first, well, before we do that, let's look at this. Notice it says the read, not write bit, or the RW bit, there's a line over the W, that means read, not write. When 0, the data is written into the device. When 1, the data from the device is read. So in other words, we can specify whether we want to read or write to that by whether we set that high for read, low for write. Now there's also this multiple/single, multiple not single bit. When that's 0, the address will remain what it was from the previous read. If you set that to multiple and set that high, it means when you read it, it'll auto increment the address without us having to send an address again. So this is a way to optimize things. So you could say, hey, start at address 10 or 5 or 0 and do a read and do another read and do another read, and it'll automatically kind of index through the memory of the register set. In other words, it's kind of like saying, having an index into that array and saying I++ on the index or index++ to move to the next one. We can control whether we want to stay where we are or tell it to move to the next one. And that's this bit right here. And the rest of that is AD0 through AD5. Those are the address value that we're putting in. So we could put in all zeros here and then do a read, and then this thing would send back to us the contents of register 0. Very clever design, very simple. Now, here's a detailed view of an SPI read. And you can see we pull the slave select line low, chip select line goes low, we clock 8 bits, which is our address word, and then we clock another 8 bits, and that's the data coming back from that. And over here, this doesn't matter what we're clocking out here. These are just clock signals for that shift register is still going to exchange values, but it doesn't matter what we put here. And in SPI implementations, a lot of time you'll see that as a dummy byte, that's dummy values going out that don't matter because we did a read. When we do a read, we're reading what came back, it's ignoring what went out. Now, there are some systems where you can write things out that matter while reading things in that matter. On this one, it's saying, you say you want to do a read, you put the stuff here for what address you want to read from, and then you tick the clock 8 more times, and then after that, you will have the contents of the register. Now, let's move on. Here's a multi-byte read where you're saying to read, if you put the multiple line high here, it says when 1, it increments the address. So you could actually tick the clock 8 times and get a byte, tick it another 8 times, get the next byte, tick it another 8 times, get the next byte, and so forth to get larger amounts of memory back from that device. Again, super clever, very cool setup. Now let's look at a write transaction. Here's what a write looks like. The write, it doesn't matter what SDO is doing, it doesn't matter what MISO is doing because we're not getting data back. It's still going to shift data back from its register. We're just going to ignore it. So in other words, we send out the address that we want. We say we're going to do a write, and then we send the data we want to write to that register, and we clock that out. And this also has a multi-byte write. But notice this is very similar to what you did in the previous lab, the Synchronous Communication lab. The only real difference here is we have another byte, or another line that as we're shifting out, it's also shifting back in. And we also have this chip select that we're saying, hey, activate that device. I'm going to talk to it. So you can think of that as kind of the chip select going low is like tapping it on the shoulder saying, hey, I'm about to send you data tick, 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 here comes the data, you're sending me data back, and when we're done with that transaction, the select line goes back high again. Okay, now what data is available to read from this? Well, since it's organized as registers, there's usually, in most SPI devices, this register map. So here's what the register map looks like for this device. Notice this byte 0, the first 7, bytes 0 through 6, it says reserved. Those are usually factory things. You'll notice that there's a status register, auxiliary status register at position 7. And so if we say read from address 7, it'll give us that status register. And then there's a temperature sensor inside of this device. So you can read the low byte of the temperature sensor, the high byte of the temperature sensor. A lot of devices like this have a who am I register that has a default value that you can read to make sure that that's that device you're talking to. So if I read from, in this case, address 0F, it'll read me back 33 hex, or this bit pattern here. It's 33 hex, which is a way for us to tell, is that the device that I think it is? Pull the select line low, read out register 0F. If it's a 33 hex, it's probably this device. Now, how do we actually read there are some control registers here and configuration registers. There's another status register down here. And now here's where the actual data from the axes come in. It's from 2.8 all the way up to 2D. And there's a low part and a high part. So those give 16-bit values. So we read the low part, read the high part. And now we have the x-axis reading from that accelerometer. We read the low part and high part from the y. And that gives us a 16-bit value for the y-axis of that accelerometer. Low part and high part for Z gives us that. And then there's also the ability to set up interrupts and configure that stuff. Now, if you want details about how the rest of this works, you can kind of look through the rest of the datasheet here, and it gives you a description of each of those things. And let's just for fun, let's go to the register that outputs the data, which is right here. So out XL, which is 2.8 hex and 2.9 hex for the low and the high part. It says that's the x-axis acceleration data. That value is expressed as a 2 complement left justified. And notice it says you can refer to section, the high resolution mode, normal mode, or low power mode, which kind of changes how that data looks. But the idea there is we're getting this data in a 16-bit 2's complement value. 2's complement means it can have negative numbers and positive numbers, and it's telling us in integer value that could go negative when the acceleration is one direction, positive when the acceleration is in the other direction, and we've got 3 axes of that. So we could set this device up and then read that data out of there and know things like, is the phone this way or is it that way? I guess this app doesn't care if it's upside down, it knows that, but it can do this way. So notice, how does it do that? It's reading the data out somewhere in this microprocessor in the phone is reading that chip over something like SPI, getting that data, and then it's making a change to the display, which the display on this is probably also driven by something, some form of something similar to SPI. But that's the basic idea for how these work. So let's go back to the presentation just for a second here. So we looked at that device. And one of the things that I had mentioned previously was that there are a whole lot of different devices like this. In fact, there are just tons of them. There's temperature sensors, which actually there's a temperature sensor in that device we just looked at. There are temperature sensors, atmospheric pressure sensors that you can use for determining altitude. Pressure sensors you could use inside of a tank or something like that to get the pressure in the tank. There's A to D converters you could use for any number of things. There are memory devices, inertial sensors like we just saw with the accelerometer, also gyroscopes, magnetometers. There are LCD screens and OLED screens that you talk over SPI to put the data out there to draw the picture on them. SD cards themselves you can talk with over SPI, wireless modules that you talk with over SPI, GPS modules, LED drivers, touch sensors, pretty much anything that you can think of. And let me go back to the desktop thing here real quick and take a look at something. So give me just a second. All right, so let me pull this over here and let me switch this back so you can see what I'm doing for just a second here. There we go. All right, this is a large distributor called DigiKey that distributes electronic components. And so one of the things I'm going to put in here is I'm just going to put SPI. And we're going to see how many matches come up. All right, so there are 113,000 matches. And you'll notice down here, there are a whole bunch of categories for those matches. So you'll have things like interface chips, memory chips, interface controllers, microcontrollers themselves that talk over SPI, specialized interface devices, adapters and converters, display modules, temperature sensors, evaluation boards, UARTs and other communication devices, data acquisition devices like A2D controllers, and things like that. And those are just the top categories. If I scroll down through this, there's just tons of things in all different kinds of categories. Fans, devices to control the fans and the temperature of things inside of a PC, for example. Tons of integrated circuits here that all are SPI-based battery controllers, codecs for turning data into sound into a stream of data and back from a stream of data and back into sound. Just tons and tons of different devices that are all SPI-based devices. All right, so let's look at a few more of these for a second here. So I'm going to go back to here, and I want to look at a couple other ones. So the first one I'm going to look at, let me go back to the presentation just for a second, and then we'll continue on from there. But the idea here is that there's just tons of these devices. So one of them, we're going to look at a few here. We're going to look at this 25 LC256 PCF 85063 BTL. And we're going to look at an Nrf24l01 Plus. Now these are just three different chips. The first one is a Eeprom, which is electrically erasable programmable ROM chips. So this is kind of like flash memory. You can store data into it, and then you can read the data back out of it. And notice that's 256K bits of memory. So to connect this, you just connect, and if you want some kind of storage on your microcontroller or on your embedded system you're designing, you drop one of these EEPROMs onto an SPI bus, and you can send messages to store things, send other messages to pull data back out of it. Very easy to use, very cool, and very easy to interface. You just got the four wires: slave select, MOSI, MISO, and the clock. That's it. And if you wanted to expand the memory, you could add another one, just give it its own slave select, connect all the other lines, and now you have twice the amount of memory. Or if you want to add an accelerometer to that device in addition to the memory, stick it on the bus. You want to add a real-time clock, you want to add wireless, stick them all on the same SPI bus. All you have to do is give them their own slave select lines. All right, let's take a look at those data sheets briefly here. So let me switch back to that memory chip first. Let's take a look at that. And let me, oh, you can't see what I'm doing, so hold on a second. All right, so there we go. So this is that memory device. This is the 25LC256, and you notice it's a 250, the description is 256K SPI bus serial EEPROM. Again, notice the maximum clock speed is 10 megahertz, pretty quick. There are memory devices that can go faster than that. And you'll notice that this is 32,768 bytes, 8 bits each byte, which gives a total of 256K bits worth of memory. And that's one thing to take a look at, that the memories tend to state their sizes in the number of bits, not the number of bytes. So in this case, 256K is the number of bits. So if we think about that, that's 32K bytes worth of memory that this chip provides. But for an embedded system, that might be a lot. That could be useful to store a lot of information. It could be like a transaction log for a security system. It could be security codes. It could be audio for playing back some simple messages in some kind of automated system that says ready and armed or not ready or whatever. There's a lot of stuff you could store in that. Now, notice that it's organized as 64-byte pages. that doesn't really concern us now. If we were really interested, we could dig into the details. What I care about is, first off, here's what the pinout looks like. It's got power, VCC, ground, VSS, but then it has a clock, an SI and SO, so that's the data in, that's the data out. There's the serial clock, and then it has a chip select. And these devices also have this WP pin, which is a write protect pin, which basically prevents it from being able to write when you select that. So you can make a device, you can say, put the data in there, and then connect that pin, and then nobody could write over it again later. Notice that, and this is kind of interesting, it'll handle 1 million erase and write cycles. It'll retain the data for over 200 years once you put the data into it. Some devices have a lower number of amount of endurance, where maybe it's like 10,000 cycles. Some of them have more, 10 million cycles. But this basically guarantees that this will work for at least 1 million erase and rewrite cycles, and it'll hold data that we put in there for at least 200 years. Probably much longer than the device will last. It'll be useful. It's unlikely that an embedded system 200 years from now is still going to be doing something somewhere, but you never know. All right. And you'll also notice it's automotive qualified, which has some requirements on how reliable it is and things like that. But it's a pretty easy to use chip, just like any other SPI device. I want to go to the actual charts that show an SPI transaction. Here we go. Here's the read sequence. And you'll notice this looks very similar to the read sequence we saw in the previous device. Basically, chip select goes low. We tick the clock a certain number of times. And then in this case, an instruction gets clocked in. And then when we tick it more times, there's an address that goes out. And then there's data that either goes out or data that comes back in. So if this is a read sequence, then notice we put in the read instruction, which is 4 zeros and then 0011. And this is a read instruction. There it is right there. And then we tick out the address, and there's a 16-bit address we output. We tick that out. And then the next 8 bytes or 8 bits after that are the data that's at that address. So in this case, we would have to do 4 total SPI exchanges while the chip select was low. We do 1 for the command or the instruction. And then we do 8 bits for the high part of the address, another 8 bits for the low part of the address. And then the next 8 after that, it gives us the data that's stored at this address. So very easy to use, very cool to do that. And you'll also notice that there's a way to write to the memory, write data to memory at the beginning for the selected address. There's also this reset the write enable latch, which disables write operations. There's a way to re-enable that. So just like there's that write protect pin that has a pin that enables and disables it, you can also enable and disable it with these special commands. And then there's this read and write to the status register commands. Now, there's a read sequence. Here's the write sequence. So there's the instruction, there's the address, there's the data, and the SO, which would connect to MISO. The slave isn't outputting anything while we're writing data to it. There's also a page write where we can write, rather than just 1 byte, a whole bunch of them. And you notice this just continues all the way up to byte 64. So you just do the same thing. You just keep clocking the data out, and you can write a whole block of 64 bytes all in one transaction. All right, and that's pretty much how this works. Notice it was very similar to that accelerometer. You just pull the select line low, clock the signal out, keep clocking it to put the address out, and then it either gives us data or we give it data. All right, let's look at another one. Let's look at that real-time clock chip. All right, so here's a real-time clock chip. This is the kind of thing that would be in some sort of, I don't know, like a security system that has a calendar in it, or maybe in your PC that it knows what time of day it is, even when it's powered off. And these chips are generally very low current. They have usually, there's a battery that operates them when the power isn't on. But essentially what this does is it just has a clock and a calendar built into this one chip. And how do we access it? Well, the data can be accessed over the SPI bus with a maximum data rate of 7 megabits per second. So this one's a little slower than the other ones that were 10 megahertz. This one is 7 megahertz instead as the maximum rate, but still very fast, especially considering this is just a clock that's keeping track of the The time, it also has an alarm function and a countdown timer function. So inside of your smartphone, when you access the thing and set alarms, or on the Alexa when you set an alarm, it's probably something like this that might be in there keeping track of that. And you'll notice that this is very low current, 0.22 microamps. That's a very small amount of current draw. So with a really small battery, this could keep track of the time of day and the calendar date and any alarms you've set for a really long time on a very small battery. And you notice it has applications listed here. Still cameras, video cameras, so when you take the picture, it times and date stamps them. A printer, copy machine, mobile equipment, battery powered devices, it lists that there. Now, what we care about though, again, the pinout, SD has a serial data in, serial data out, SCL, and a chip enable. And the part that I'm interested in is the kind of the transaction sequence here. That's a reset. It almost always is a chart that shows the SPI transactions. Maybe this does not have one, but we'll find it if it does. Okay, so here we are with the SPI bus write and an SPI bus read example. Now, this chip is a little strange in that the select line is active high instead of active low. And that's could be a problem on some systems, but this one, it turns on when we pull the line high rather than low. And again, the only way to know what rate the chip supports and how that transaction happens is to look at the data sheet and make sure it works the way you think it is. So in other words, with this one's line, enable line, we would keep it low and we would set it high and then perform that transaction. And you'll notice that this kind of follows the same methodology as the previous one. Now let's look at one more, which is actually a chip we're going to use to do some stuff in this class. And that is this Nrf24l01 Plus. Now, with these chips, these are actually 2.4 gigahertz wireless chips. And these chips were actually designed to implement things like video game controllers for like the Xbox 360. So in other words, they have this thing where you can put data in a packet and it'll send it wirelessly, it'll receive it on the other end, and it has a kind of this really cool feature where it auto acknowledges. So when you send data, it can say, yeah, I got that. But these are designed to be really simple. Notice in the application section here, let me zoom in on that a little bit. Wireless PC peripherals, mouse, keyboards, and remotes. Game controllers is listed, voice over IP headsets, sports watches and sensors, asset tracking systems, toys, a whole bunch of stuff that's listed in here. And these are actually pretty cool chips that have pretty good data throughput rates. But essentially you make a packet and you send it, and the other chip, the same kind of chip on the other end, receives that. It does something with it. But how do we talk to this chip? Well, SPI. So let's look at that. All right, so here's the part that I'm concerned with here in the data sheet for right now. Data control interface, SPI. So let's just go to that page 50 and take a look at that. And you'll notice that it says data and control, or the data and control interface give you access to all the features in the chip. Data control interface consists of the following 6 5-volt tolerant digital signals: IRQ, CE, CSN. And notice this says SPI signal, SCK, SPI signal, MOSI, SPI signal, MISO. So there's the 4 SPI lines. And there's also an interrupt line that you could configure, so when you receive a packet, it pulls that line to say, hey, the packet came in. There's also this chip enable that's used to turn on the transmitter and receiver section of that, so you can power that up and down. So that means you could keep it powered down so it's not using current to talk over wireless, but you can still configure things over SPI and then activate the radio later. So this is kind of like a radio enable. This is an SPI chip select that lets us talk to it. So really, it's just these 4 lines to communicate with this chip. Now, essentially it says using 1 byte SPI commands, you can activate the data FIFOs or the register map during all modes of operation. Now, this goes up to 10 megabits per second, just like those memory chips we looked at in the accelerometer. And that's a pretty common thing. There are SPI chips that will go faster, like 20, 30, 40 megahertz. But these ones will go up to 10 megahertz. And it says functional description. The SPI is a standard SPI with maximum data rate of 10 megabits per second. And then this describes that. So what I'm going to do in this case is look at here's the set of registers and commands. Again, it's just a binary word that you put into that register when you shift it out, and it tells what we want to do. And there's one for reading from one of the registers where we give the register address. There's one where you write to a register and give it the address. And then there's reading the payload, writing the payload, or read the receive payload, write to the transmit payload, flushing the transmitter, flushing the receiver, and so forth. There's this stuff about acknowledging the things. Now the registers themselves is a whole register set that has a status register and other things. Let's take a look at those quickly. But before we do that, here's the SPI timing diagrams. Here's a read operation. Same thing. The line goes low. The clock ticks 8 times, which has our MOSI data goes out. Also notice that as the MOSI data goes out, the status register contents come back. We get that kind of for free. And then after that, this is the data that goes along with this command here. Because we're doing a read, we're saying, hey, I want to read. Here's the data that goes with that read. And then for a write, it's the same thing. But the data comes, there's the status register going out, and then here's the data going from the master to the slave. And notice these are grouped into blocks of like 8 for each one. So the idea here is this works just like all the other things did. And if we were to want to look at what do those registers actually do, well, here's a list of all the registers. There's a register map, just like we had for the accelerometer we looked at. And this register map, you'll notice register at address 0 is the configuration register. Register at address 1 is this enhanced shock burst register. Register at 2 is the receive address register. So we can give these things different addresses. The register at 3 is the setup of address width. How big is the address field of those packets? And every one of these is just labeled and it describes what they do. So what we're going to do next class is you're going to actually talk to one of these devices and get it to do things. Now, as a quick overview of this, I have some of these for you to use. So next class, we're going to have to figure out a way to distribute these. So for next class at meeting on Wednesday at the normal 2 o'clock class time, I'm going to be down at my office and I'll be able to distribute these. But if you want to buy your own, because we're going to use these for several labs here, and we're actually going to get we're going to get it where we can talk to these chips, and then we're going to get it so one of them can communicate information wirelessly with another one. And we're going to do that by talking SPI to these chips, which is going to be pretty cool. So you could actually make a wireless system, like a wireless embedded system, that a security system, a toy, or something like that, that actually talks between these. And let me quickly bring up what these modules look like. So I'm going to go to Amazon here real quick. And I'm just going to put in Nrf24l01, which apparently didn't type in there because Edge is stupid. I'm going to put module. All right, so here are these modules. Notice that you can get 10 of them for $12.88. So they're about $1.20 each. You're going to need 2 of them for the lab. So if you guys want to get together and buy some of these for yourself, you can. There are also long-range versions of this, like you see down here, with those 2 that have this external antenna. You probably won't need those. And you'll get decent range out of these ones, the little $1.28 ones. Within a room or a house, you'll be able to have these talk to each other. But if you want to have something that goes a longer distance, like a couple half mile, couple kilometers, then the long range ones work as well. But for now, you could just get, for example, like these ones, and those will work. Those will work great. And if you don't want to buy those, I have some available. Just come to my office hours on Wednesday. I'll hand them out. And next class, we're going to have that lab. I'm going to give you that lab sheet. I'm going to talk all the video that talks about how we're going to do that, how you're going to wire these. And then you're going to, the first thing is though, you're only going to need to wire one, and you're just going to use SPI to talk to that chip and read out contents of the registers. That's all you're going to do. For the lab after that, we're going to set up those registers so one of these can communicate and talk to another one. So you're going to be able to send a wireless signal. It'll go out of one of the antennas on one, go into the antenna on the other, and from one Arduino to another Arduino, we're going to be able to pass data from one end to the other end. Pretty cool stuff. And how can we do that so easily? Well, SPI is a standard, and we're going to get our Arduino to talk SPI to that chip. Now, quickly, let's go back to the presentation here and finish things up. So note that if you know how SPI works and you're designing a system, that opens the door for you to add temperature sensors and pressure sensors and all kinds of things if you know how SPI works. Real-time clocks, memory devices, wireless devices. And when they're designing something like a smartphone, that's how a lot of those things configure, including the touch screen, including the fingerprint sensor on here that lets me log in with my fingerprint. That's an SPI device inside there. Okay, there are some other variants of SPI that are probably worth mentioning. For example, there are what's called dual data rate SPI, where it transfers on both the rising edge and the falling edge. And those will be labeled like dual data rate SPI or DDR SPI. There's also what's called quad and dual SPI. Quad and dual SPI is those just add additional data lines. So rather than just having one MISO and one MOSI, you might have 2 in the case of dual SPI or 4 in the case of quad SPI. And when the clock ticks once, 4 bits get exchanged or 2 bits get exchanged rather than just 1 bit being exchanged. So think of it like 4 shift registers all connected, and you can move 2 times or 4 times as much data on each clock tick. And SD cards use a version of something like that to have them be faster. Most SD cards, you can also still talk to them with a single shift register with 1 MISO and 1 MOSI, but they have a mode where you can make them faster and push out 4 times as much data, both out and in at the same time. But in all cases, they're all synchronous. They all basically have that clock, and they all work in a similar way. Different devices, as we've seen, have a maximum clock rate allowed, so if speed is important on your design, make sure to look at that. If you need something where the memory is incredibly fast, then maybe you want a 20 megahertz or 30 megahertz SPI interface, and maybe you want something that supports quad SPI to move more data at once. But one thing to note is even though there's a maximum allowable clock rate, there's usually no minimum. In other words, since all that matters is when that clock ticks, you can run SPI things fast sometimes, slow other times, really down to as slow as you want. So one thing though is let's look at how you'd implement SPI, and this will be the last couple things we do today. And that is to implement SPI, it's often implemented in hardware using special shift register hardware. But if we're on the microcontroller side, we can also implement what's called soft SPI, which is kind of like a software implementation, just like we did with our previous synchronous communication lab. And really, we can get away with that because the clock rate can run slowly or quickly, and we can handle that in software by putting in delays or taking out delays. So let's look at a simple software SPI function implementation. So here's a simple software SPI implementation. This is based on code that I had written and have used quite a bit. It's a little bit abstracted here, but not too much. But notice that we create this software SPI function. We pass in a character, an unsigned character. In other words, 8 bits get passed in, and it returns to us 8 bits. And that's what we're passing in, what's going in our shift register. It's going to clock all of that out, and whatever clocked back in, it's what it's going to return to us. So essentially, the way this works is this for loop starts a bit mask at 128. So in other words, 8 bits, all 0 except for the most significant one high. You could also put 0x80 there. So 80. And then our bit mask, we're going to run that while it's greater than 0. And then each time through the loop, we're going to shift it over 1. So the first time through the loop, it's going to look like this. We're going to look at the most significant bit. The next time through the loop, it's going to go to there, and there, and there. We're just going to ripple that down till it gets to the end. And then when it ripples off the end, when we shift there, it goes to 0. That's what stops the loop. So this is going to go through all 8 bits, starting with the most significant, going down to the least. Now what we're doing down here is we're saying, hey, if that bit at that position is high in the data we passed in, then set the output line high. In other words, that's the bit getting shifted out. Set the MOSI line high. If it's not high, set it low. So we're forcing the MOSI output line to match the state of the bit we're currently on. And then we have our delay and our clock going high to tick the clock high. And then after we tick the clock high, we read what came back on the MISO line. And if it was a 1, we OR it to, or the bit mask, the same position we're on, with our input character that's coming in from the other end. And so in other words, we're going through each of the bits one at a time, and we're ORing them all together to make the result of what came back in. There's our delay and setting the clock low to tick the clock, and then we go to the next bit. So in other words, for each clock, we're putting data out, ticking the clock, reading what came back from the slave device, finishing the clock tick. And once we've completed that, we'll have all 8 bits will have exchanged from master to slave. We're going to return what came back from the slave, and we've shifted out what went to the master. So really small amount of code, really simple to implement, pretty easy to understand. So let's go through this. So we go through each bit from most significant to least significant. That puts the current bit value and what we're trying to send on the MOSI line. We tick the clock. We then read and store the bit value that came in from MISO. We finish ticking the clock. And then after we repeat that 8 times, we return the byte value that was received after we sent out the byte value that went out. So notice this function is implementing that full duplex. For every byte we shift out, we get a byte back, and it returns it to us. And you're probably going to want to use code like this for your next lab that we're going to do next class, the one we're going to talk over wireless. This is a good thing to build upon that. Now, a couple things to note with our SPI function. Like I said, we always pass in a byte value. It always returns a byte value. Those are the shift register going out and the shift register coming back in. Now, note that one thing we haven't done is there's nothing in there about the slave select line, so we would need that in some other function to say, okay, set the line low, shift this byte out, read this byte back in, set the select line back high again. So in the next lab, we're going to implement that. We're going to write some code to talk to an SPI device, specifically one of those wireless modules. If you want to order your own, feel free to get them from Amazon. They're cheap. You guys can get together as a group and say, hey, it's $1 a piece. We need 2 of them, $2, and you have the ability to make these Arduinos talk to each other over wireless. Pretty cool. If you don't have them, talk to me. I'll get you ones to use. And actually, I'll place an Amazon order today and get another dozen of those or so, maybe 2 dozen of those in case, so I don't run short considering some of you are working remotely. So if you aren't coming into school, order your own. Just go to there and again, go to that maker focus is the ones that I've ordered before and they work. That's pretty much it for today. Finish up your lab 4 to get ready for lab 5. There's some similarities in those 2. And next class, we're going to be talking over SPI to that device. So that's it. Everybody stay safe. Wash your hands. Wear a mask if you're out doing stuff around other people that aren't from your household. And next class, we're going to have a lab. We're going to implement some SPI and have an Arduino with its microcontroller talk to a real-world wireless device over SPI to access those registers and do things with it. And then we're going to, the next class after that, we're going to talk about I2C a little bit, which is another competing technology to SPI. I want you to be exposed to that. We're probably not going to do a lab talking to an I2C device, but you should at least be exposed to that. And then we're going to do a wireless lab where you guys are going to make those NRF modules talk over wireless. And again, those chips were created for things like video game controllers. So this is kind of when you're playing the Xbox 360 and moving the joysticks and hitting the buttons and pulling the triggers, that's the kind of chip that's actually relaying that data from the controller, the wireless controller, to the actual console. Same thing for PS4, although a different chipset for that. Okay, that's it. And if you want, I've posted a zip file with those data sheets. If you want to go through and look at those yourself and read up on those, specifically the Nrf24l01 Plus, which we're going to be using going forward, I would encourage you to take a look at some of those data sheets and play around with them. Other than that, that's it. Everybody have a good day.